All right, let's keep going. All right, so now I laid out this really impossible problem that you guys have to solve. So now we'll start teaching you some of the tools. And first I'm going to try to just give again, an overview of what we're doing. So suppose that you were trying to decide on, say, some new transportation fuel, and you decided that you would make it out of carbon, hydrogen, nitrogen, and oxygen atoms, because that's what we decided are the good elements for a fuel. And you wanted to simulate the behavior of a combustion system with this fuel on a computer. What do you need to know to make a model that you would be able to use it? Like, what are the inputs to a solver like ChemKin or Cantera? Yeah?
The thermodynamic properties of the different species.
Do you need the thermodynamic properties of different species? That's one thing. What, transport properties? The transport properties of species? Yeah?
The reactions that make up the model.
You need a list of all the reactions that are going to happen?
With the Arrhenius
yeah?
The concentration of each species that's present.
So like maybe the initial concentration of each species or what's flowing in? Yeah?
The temperature profile.
Activation.
The temperature profile or maybe heat losses inside your system? Yeah? Pressure? Yep. Yep. The geometry of the reactor? Yeah, the flow field? Yeah.
The residence time.
Residence time? Yep. Okay, so these are the things you need to know. And so we have to figure them all out. And actually from the very beginning, you have to know which species you have. So you have to know what's coming in, but you also have to know all the intermediates that exist inside the system, and then all the reactions involving all those species and everything. So even for the simplest fuel, this turns out to be quite complicated. So this is the model for hydrogen with oxygen. And these are the 10 most important reactions. And actually the accurate models have about 10 more reactions. And it's just a hydrogen and oxygen. You wouldn't think it would be that complicated, but actually it is. And then you need to know the thermo of each species, transport properties of each species, the rate coefficients for every reaction. Many of these reactions depend on both temperature and pressure, so you need to know both of those things. So this is actually quite a lot of information you need to know about your system. And if we get to more realistic fuels that have a lot of atoms in them, not just H2, this list gets to be quite enormous of the number of different reactions. And so when we're doing chemical kinetic modeling, we're really trying to predict the rate of change of the chemical species in the model. And we have to worry about reactions and also diffusion and convection, because they all affect the concentrations of the species. And when we change the concentrations, they also change the enthalpy, right? The chemical enthalpy. And so the total enthalpy is constant. So what happens is the temperature changes too. So you have to worry about the energy equation as well, which is completely coupled with the concentration equation because the chemical energy terms are really dominating, driving the temperature. This first term, the reactions term, is usually called omega, this symbol here, and that's the rate of change of species I just due to reactions, not including any transport stuff. And then that's usually a sum of several reactions that involve that species, because usually that species will be consumed several different ways and also can be formed several different ways. And so you have to add up all the different reactions that involve that species with the right stoichiometric coefficients, negative signs if it's a reactant, positive signs if it's a product. And you add them all up and you get omega. And the chemists in the audience might be tempted to write dc dt is equal to omega. Please don't do that because diffusion and convection are really important also. And in a steady state burner, for example, they all are basically equal to each other, right? Because if it's steady state, the right-hand side must sum to 0. So they're typically that the reaction term is the same order of magnitude as the size of the diffusion and convection terms. And most of the combustion systems are quite inhomogeneous. So the concentrations are different in all the different spots, and many are also changing with time at each different spot. So it's quite a complicated scenario, and typically it's open. Usually we have fuel coming in and we have exhaust coming out somehow. Or we're in a piston and we have a time-varying volume. It's another common thing. So all these are definitely not the simplistic closed system scenario. It's usually some quite complicated scenario. Reactions are reversible by the second law of thermodynamics. So we have a rate of a reaction, and it's like a forward rate of that reaction and then minus the reverse rate. This is like the net rate of the reaction. If you have an elementary step reaction, typically the forward rate can be written as a rate coefficient times the concentration of a reactant or a couple of reactants multiplied together, like this. And this K of T thing is called the rate coefficient. Some people call them rate constants, but it's kind of misleading because it's obviously not constant because you change the temperature, it's different. And typically in the combustion system, the temperature is varying over quite a gigantic range. So the same K has wildly different values in different spots at different times because the temperature is all over the place. So the right way is called rate coefficient. But it is a physical constant in the sense that at that temperature, anybody who measures that reaction will always measure the same K. They're measuring the same physical quantity. And in fact, it's a quantity you can predict from first principles calculations. So it's not like an purely empirical thing. It's really fundamentally based. We know what it really is. It's just kind of complicated to calculate. But we'll talk about how to do it. All right, so suppose you have this reaction. And so it's H plus O2 to OH plus O. This is the most important combustion reaction in most burning systems, ignited systems. And it's important because on the left you have one reactive radical, and on the right you have two reactive species, and this O atom typically attacks the fuel and makes an OH and another fuel radical. So typically you have one reactive radical in, and you often get three reactive radicals out. And so that's what's called a chemical amplifier. It amplifies radical concentration. So if you have some radical concentration, if you have this reaction operating, after some time, you'll have more radicals. And most of the combustion reactions are catalyzed by radicals. So as the radical concentration goes up, the rate of everything gets faster and faster and faster. And this was what leads to explosions, for example. So you watch those nice special effects in the Hollywood movies. It's because they got some gasoline, they mixed it with some air, and they got a reaction going like this and went kaboom, right? The rate coefficient, you can write it in the Arrhenius form. This was derived empirically by Arrhenius back in the 1800s. And it's found out that's not quite exactly right, and this form works a little bit better because it's a kind of a weaker extra T dependence on top of the Arrhenius one. But the Arrhenius T dependence is a dominant thing. This A is called the Arrhenius A factor, EA is called the activation energy, N is the tetrahedral exponent, and the R here is the gas constant. And then the K can also depend on the pressure too. And one big aim of chemical kinetics community is to try to figure out these numbers. What's the A, what's the EA, what's the N for some particular reaction? And sometimes we really care. Like for this reaction, if you change this K by 10%, you get wildly different predictions of what would happen in a combustion system. So it's really, really important number. And we have things called the order of reactions. That's like this is a second order reaction because it's a product of two concentrations. And the units of the A factor depend on it. So for a first order reaction, A is units of just per second. For a second order reaction like this, the units of K are volume per mole per second. And in combustion, temperature is always Kelvin. So where does this Arrhenius dependence come from? It comes from the Boltzmann population of a thermalized system. So if I have, I'm at a temperature T1, the Boltzmann factor really favors low energies. So most of my molecules have very small amounts of energy, but a few of them have so much energy that they might be above a reaction barrier and react. And so these small fraction of all the molecules are the ones that are wiggling so violently that they actually can break a bond, say, or make some chemical reaction happen. And those are the ones doing everything. But that population scales as the Boltzmann factor. And so it's the barrier to the reaction, and then these are the molecules that have energies above the barrier, the ones that can react. If you think about it kind of physically, the barrier is like how much energy would it take for you to push, say, this boulder up over the hill. That's how much, what the barrier means. In a thermal system, you don't have to push them. The thermal fluctuations are just making the boulders wobble around, the atoms wobble around, and sometimes they get so much thermal energy that they actually get over the hill. If you increase the temperature, the Boltzmann factor is a different shape, and it has more molecules that have energies above the activation energy, and so you get a higher rate. Here's the math to how to write it out, the equation as a matrix of stoichiometric coefficients times the rates. When we're trying to make the models, there's like a lot of different aspects we need to worry about. You have to have chemistry that has enough detail to cover all the phenomena that you care about in your simulation. So in combustion, a lot of times we care about ignition. So we have to have the chemical reaction supporting around the ignition point. But then once the ignition happens, the temperature jumps up. And then you have to have high temperature reactions that are relevant at that condition. And then as the reaction proceeds, all the fuel's consumed. And all you have is like a lot of exhaust stuff and secondary products. And you have to have all these reactions of secondary products. And so if you wanted to simulate that whole thing with one chemistry model, you'd have to be sure that you had all those reactions are relevant for all the different stages of what happens in it. And so this can be quite a problem because the number of different reactions you need to have in your model could be quite enormous. And hard to make sure you didn't miss one, and hard to make sure you have good expressions for the Ks and the thermochemistry for each one. So one direction people do is they say, well, let's just consider a smaller range of conditions first. So let's focus just on the already ignited case. So we don't have to have ignition chemistry in. Everything's always hot. We only need high temperature chemistry. And we can write a little model about that. And let's start with maybe just a case where it's fuel lean. So all we have is that the fuel is disappearing and making CO2. We don't have to worry about forming soot or pyrolysis products because if we make them, they immediately burn away. Then later I make a different set. I say, well, now I really care about soot, so I'll try to work all about pyrolysis chemistry, and I'll try to worry about what would happen if I don't have much oxygen, and mostly I'm just cooking the fuel, what would happen? And you get all these different intermediates that lead towards soot, and then I can try to take the union of those two sets of reactions to make a bigger set that might be able to cover both regimes. That's the general strategy of how this goes. And then later, maybe I want to add the ignition chemistry too. So I'll add all these low temperature reactions, see what they do. Then later, somebody cares about the emissions of some byproduct, N2O. Also, people worry about N2O because it's a greenhouse gas. So now I have to figure out, make sure I have reactions that lead to N2O in my model as well. So you can imagine this goes on. And if you read in the journals, like Combustion and Flame, you might have like the same fuel, might have 100 models published, where they started with one that just gave you the heat release rate and made some CO2, and then you got one that made the soot formation, you had another one that made some NOx, another one that made whatever, and then somebody found all the mistakes in the first model, so they published another paper to publish the corrected version, and it goes on and on and on and on. And that's the progress in the combustion chemistry field is like that, where you never really reach the end of having the perfect model that does everything right. And so it's a whole iterative procedure of trying to figure out to make your model cover a broader range of conditions and of observables that you might care about, and then also trying to make all the numbers better and better. And then also just correcting omissions and mistakes you had in the earlier models. This challenge of how to get the right numbers is really hard. And a lot of people in this community, that's all they worry about, is like how to measure or calculate really good rate coefficients, how to measure or calculate the equilibrium constants for certain reactions really well. get the thermochemistry really accurately. And that's actually very complicated. There's whole conferences just about those topics. And then there's another whole set about when you put them together, you need to worry about the uncertainty in each parameter and then how that uncertainty affects the uncertainty of the overall simulation. And that's also quite a complicated story too. When you do this and you get the chemistry good enough that the chemists like me are happy, typically the mechanical engineers are really unhappy because the model has gotten so large that they can't fit it into their computational fluid dynamics solver. And so they want to do model reduction to try to get a simplified model that they can actually solve. And so the chemists work really hard to get a list of 1,000 species and all the details about everything, and then the mechanical engineer says, I can only handle 100, so they squash it down to 100 because they'll fit into their computer, and then the poor chemist feels like my poor 900 children got killed off. But anyway, that's what they have to do, and then they have to make the chemistry solvable. So there's some details about the chemistry that can make it really difficult for the numerical solvers to handle. So they have to do special tricks to try to get a chemistry model that's suitable to solve. And then when you do solve it, it never matches what the experiment said anyway. And so then you have to figure out why did the simulation not match the experiment. And that could be that the experiment was wrong. It could be that the numerical solve was wrong. It could be that the model reduction was wrong. Or it could be that the chemists were wrong in the first place. And so there's many possibilities. And yet that's a project to figure out what causes discrepancy. And then after you do it, then you figure out the discrepancy. You want to go back and fix it. So then you make the next version. And that's like the progress of this field. And because we never have the final model we think is perfect, and even if we did, probably we couldn't solve it in the real geometry. We're always in this unsatisfactory situation that we have a model we think is kind of good, that kind of is helpful, but we don't expect it to exactly match anything. And then the experimentalists might feel the same way because they can only measure certain things in certain situations. And it might not be actually the thing that's relevant for the technological device, right? Because what we care about is like the truck drives and works at all conditions. But in the laboratory, maybe we can't achieve all of the conditions you have in the truck engine, or you can't measure the reactive intermediate of interest at the exact condition that the truck engine's operating at. So for example, in experiments, often we work in low pressure because some of our techniques work really well at low pressure. But of course, in a truck cylinder, the pressure is really high. And so we have some problem to do with this. So anyway, that's the reality of the world, is things are not ideal. And we just have to figure out the best we can to use the information we can get from the experiments and the things we can calculate and the models we can make and solve and try to bring it together as best we can to really guide the development of the technology, to guide the development of the devices that are really going to work. Ultimately, that's the success, is you actually have a truck that works with a fuel that works. That's success. It's not exactly whether all the simulations work perfectly. The goal of the whole simulation process is to try to accelerate the development of the actual devices that people are really going to use. So anyway, it's quite a complicated thing. And if you go to the Combustion Symposium, there'll be 1,000 talks about different aspects of this problem. All right. So this is super complicated, as I said, and because of that, there's like several whole books about this. So I'm kind of showing a lot of arrogance to even try to teach this in 15 hours. But I recommend if you're trying to be serious about this field, you should read these books. There are really, really good chapters about all the different aspects of building the models and how you tell if they're good and how you solve them. So I highly recommend. All right. So quiz. All kinetic models are approximate. They all neglect some minor species and some minor reactions. And actually, often the author of the model might not even be aware that those minor species or reactions even exist. But then, on top of that, sometimes people intentionally delete the species and reactions that makes the chemistry model smaller and further from the truth because they're deleting species reactions that actually do exist. Why do they do that? Yeah.
Make it like more computation efficient.
That's right, exactly. You said to make it more computationally efficient. That's right. So they got the real model. They said, rats, my computer program's not good enough, or my computer budget's not enough, I can't really solve this, so let's just simplify it down. Is there any other reason why you might want to simplify it down? Yeah.
Maybe they want to catch a specific phenomena, let's say like ignition delay time, or like laminar flame speed, so there is need to include the formation.
Yeah, so sometimes your model is very ambitious to predict a lot of things, but maybe your actual application is much simpler than that, so you don't need to have all that stuff in there, and it's just chewing up computer time for no benefit. Yep.
I'm just going to build on that and say that you're able to accomplish or meet the parameter that you set with the models that you have included. So it might be that there's a fraction of some species that you're not really concerned about, and so you resolve the information.
Yep, so sometimes you might just say, I'm a mechanical engineer, I don't really care about all this stupid chemistry stuff. Let's just erase off a whole bunch of it. It's good enough for me, it works. That's a very practical thing to do, yeah. It's one more thing. Yeah.
If you want to hone in on a few key reactions, and the minor reactions are taking and producing the same reactants as those major reactions that you're interested in, so simplify the system.
Yeah, that's right. So idea is to simplify, not really just to make the computer be able to solve it faster, but actually to help your understanding, right? That when you have too many reactions, that you can't even look at the list too long, it's like mind-boggling for the humans. But if you can write a smaller model that captures all the phenomena and that you care about, and is small enough that you can actually understand it, it's very helpful for human understanding. And in fact, I would say that the people who actually design the trucks or make the new fuel, they don't want your 10,000 species model, right? They just want to have like some rough idea of what they should do to make a better truck or make a better fuel. And so they want the simplified, abridged version, the cartoon that'll help them to think of what experiment to do next, not the whole full complicated detail. And actually the same, not just about chemistry, but about the CFD. Those of you going to the CFD lectures is also super complicated. And again, the guy designing a truck might not really care exactly whether you use law of the wall or if you use some other subgrid model or whatever. They wouldn't even know what you're talking about, right? They just want to have some idea about where it's hot, where it's cold, where's the exhaust accumulating, stuff like that. That's all they want to know. They didn't really care about exactly the detail of why. And it's the same with the chemistry. Yeah, so as I said, there's many different models for the same chemistry. You can have a perfect fidelity model, where you have a very, very large number of species and reactions and the true thermo. And this is like imaginary. It's like we're the ideal, the paradigm. Somewhere, God knows the perfect model of the real reactions that are really happening. I unfortunately am a finite human. I don't know it, right? But I'm trying to achieve this. So that's like, there's one subfield of this thing that's the detailed chemistry people that are really trying to make the highest fidelity model they can. They want every number to be as close to the true value as possible. They want to have all the real reactions, all the real species in it. So my group in particular has been like promoting this view about how to do it, right? And in some cases, like hydrogen and oxygen, I think this is actually the right way to go. It's like you really can do it. You can write down all the reactions. You can get really good numbers for all the steps. It's very, very sensible to go ahead and do the high fidelity model for it. And it's also compact enough that the solvers can handle it. But then you have a lot of cases where it's completely impractical. The high fidelity model would be just so complicated that you won't be able to handle it. And so you really want is a reduced model. And one way to do it is if somebody's already tried to make a detailed model, you can just try to squash it down. So that's like one way it's done. You can also try other ways to do it. When you make the reduced model, what happens sometimes is you get rate expressions that don't follow the mass action law. because they're kind of either derived from steady state relations or they're kind of empirical. That you put in some reaction with some goofball law that just happens to match the experiment. And this can really reduce the computer resources requirements a lot. And it can also be helpful for understanding. But I would say it also can sometimes mislead you because you might accidentally leave out something that's crucial and cover it up by how you tweak things. And then later you're confused at what's happening because you had already deleted that out of the model. Third idea is just completely empirical. So I'm sure that when Otto and Diesel were inventing their first engines, they had no idea about all these reactions. They haven't even invented the radicals. That hadn't been discovered yet at the time that they were working on it. So they really had no idea. So they just like empirically said, oh, I changed the air-to-fuel ratio. I see that the ignition timing shifts whichever way. And they had some empirical relation. And they just used that to do it because that's all they could do. And we have different modern variants of the same thing where you can do an experiment, you can fit it to something, but you really have no idea exactly what's happening fundamentally. Still can be pretty useful. And then usually we have different models for different reaction conditions because it's really difficult to make one model that can cover everything. And then this issue with I think it's a positive thing that we iteratively make the models better and better with time, but it can lead to a lot of confusion when somebody, today cites a paper from 8 years ago and grabs, reaction 427 out of that model and uses parameters today, and maybe was not aware that since that time, it was found that the number was wrong, and there's another paper published with the correct value. Now they've repeated the incorrect value now in a modern publication. The next person reads it says, oh, this is from 2024. It must be a great paper. I'll use the range for reaction 427. And they don't read the footnote that said that this actually came from an estimate from 1918. And so it could be completely wrong. And this is actually, unfortunately, kind of endemic in the literature that earlier mistakes keep getting rediscovered and then repropagated. And particularly as the models get very large, the authors of the models can't even spend enough time to really carefully understand the sources of all the numbers they're using. And so this can be this is like a data management problem. And then there's just errors that propagate completely nobody knew. So for example, the heater formation of OH, people did a pretty good series of experiments, determined the number, published the heater formation of OH. It was in the NIST web book. It was in JANF tables. And then somebody found out that the interpretation of some experiment a long time ago was incorrect, and actually the heater formation was different for OH. That was like a nightmare, because in the subsequent time, everybody had assumed OH had a certain heater formation and had built all of the models on that number. And now all the models were wrong because the number was wrong. And so that was like a total chaos of trying to figure out. And so people have been trying to figure out ways to automate updating so that the models can be more like alive, a living document, not just published once when you put it in the SI of your paper, but is a thing that like automatically had links. If somebody finds a mistake in that, it would automatically get updated. It'd be much more convenient. But right now we're still stuck in the way where a lot of things are like frozen in time. It's at the moment you publish it, that's the model. And then it doesn't matter if tomorrow you found it was a mistake. Too bad, it's already published. And that's it. Okay. Quiz question. In all the chemistry models, the main purpose is to compute the concentrations of species, of chemical species. What is a chemical species? Yeah?
It's an element of a chemical reaction.
So it's the thing you wrote down in the model. But what is it? I mean, we should be able to like measure it, right? If you're predicting concentration of something, you think it's observable, you'd be able to measure it. What is it?
which different atoms are combined and structured
Okay, so he says it's like a geometrical arrangement of atoms.
of different atoms that come up in our reactions.
Okay, so certain geometrical combinations of atoms are stable enough to be formed that you can identify them? Okay, that's the definition of a species. Okay. Yep.
These are either metal stable or stable species with elements or molecules which tend to have negative heat of formation.
Okay, so many species have negative heat of formation. I'd say it's many, but not all. Yeah.
I want to just add that they don't need to be stable. They can be stable or non-stable. That just like it can be like radical.
Yeah, so definitely in the model, some of the species are stable and some of them are not stable. They have very short lifetimes sometimes. Yeah. All right, so let's think about this some more. There's kind of two different mainstream views about this. So one is the experimentalist view. It's like I have a detector and it gives me a certain signal, and I think this signal is related to this arrangement of atoms. And I call it a species. But really, I can't see the arrangement of atoms. All I can measure is the signal, right? So I have a chromatograph, or I have a mass spec, or I have a IR laser, and things that give signals there, I'm going to call the species. And so like in chromatography, I do a lot of chromatography. I see things elute and make a peak at a certain elution time after I inject it, and I say that that is species whatever. And I might be able to corroborate that by introducing an authentic standard. I might be able to measure its mass spectrum or its UV vis, depending what kind of chromatograph I have. I get some idea that there's a species. And for sure, every time I repeat the experiment, I always get some bump at that same time afterwards. So I think that's like a species. Or the mass spec, I see that there's a certain mass formed. Maybe together. Maybe I find the mass is formed after a certain elution time. Spectroscopy, I have a certain laser and I tune it, and there's something that's absorbing this certain wavelength, and I see it, or fluorescing from that wavelength. But then I do know that sometimes this is confusing because occasionally I get convolution problems where I have two different things I think are two different chemical things. They both elute at the same time or absorb the same wavelength. So I'm not really 100% sure what the species are exactly, right? That's the experimentalist view about it. The theoretician's point of view is like I can see the atoms because I drew them in my quantum program. And so I say that I have certain geometric atoms, I call them a species. So I say it's OH if I have an O next to an H and their distance is less than 1.5 angstroms, I'll call it OH. If it's more than 1.5 angstroms, I'll call it H plus O, right? And if they're within a certain distance, now I say, no, now I call it OH. I have a new name for it. Okay, but I decided, whatever distance I think was OH. Or I define this as a valley in the potential energy surface, so I can compute the energy of O and H as they come together. And I can say, wow, everything that's way down in the valley is OH, and the ones that are up above the dissociation limit are really far away, then I say that they're O and H separately as two different species. That's the idea. But you can see that now I can see there's a possibility for some inconsistencies here, right? And this is not just in atoms or molecules. It's also with people. So we could try to say, well, what's the population of Princeton? What's the concentration of Princeton stuff? And it's like, I could say, well, there's how many people are in Princeton today? Or what's the year-round average number of people in Princeton? Or the residents of Princeton who pay taxes? Or the amount of people in Princeton who are counted by the US Census? Or how many people are in the Princeton metro area? I might include Lawrenceville too, because it's really close to Princeton. I'd say, well, that's basically Princeton. Or people who slept in Princeton last night. That could also be different, right? And those would all be reasonable ways to define the number of people in Princeton. But they're not exactly the same, and they would give different numbers. And this is the same thing happens with concentrations of a species. There's like different ways you could define it they could all sound perfectly reasonable. They might all give similar numbers, but they're not exactly the same thing. And if you change the definitions, you might get something different. And typically the experimentalist definition and the theoretician's definition don't agree. So they wouldn't give exactly the same result. Now, the potential energy surface is kind of helpful for this purpose. So to a good approximation, the potential energy of any system containing atoms just depends on the positions of the atoms. So where the atoms are, how they're geometrically arranged. Certain geometrical arrangements have low energies or stable. Certain geometrical arrangements are very high energies or unstable. And you can compute this using quantum mechanics and get this number. And then you can vary the R. You can move the atoms and you can recompute it and you can see if the energy is going down. And there's typically some regions where they all give very low values of the energy and they're like down in the valley. They're like the stable geometrical arrangements. And then there's ones that are higher, they have the unstable arrangements of the atoms and they have much higher energies. But then there's a lot of trickery about this. So part of it is like if you take the atoms and just slide them along, that doesn't change the energy. Or if you do a rotation, it doesn't change the energy. So you work in a subspace of R, so it's a little complicated. And we can do classical mechanics and say, well, the probability that you have a system have a certain arrangement R of all the atoms is just the exponential of that energy divided by kB over T. That's how you'd expect it to scale. And so because of this Boltzmann factor, that's why the molecules like to spend most of their time down the bottom of the valley, because that's where you have a high Boltzmann factor. And then if you have valleys that are separated with regions of high V, then you'd expect it to stay in the valley. So maybe I draw a picture, maybe it would help. Maybe find a piece of chalk. Yeah, so if I draw a contour plot, so this is down the valley. So this is the lowest V of R. This is V of R. And here I'm drawing it. And this is like R1. This is R2. In the general system, there's a lot of R, so all the different positions of all the atoms, X, Y, Z of all of them. But just say 2. You can see like there's a valley, and then there might be another valley over here. And I might call this species 1 and call this species 2. And maybe there's like some high energy contours. So to get from here to here, I have to like go over this mountain ridge to get there. And so then I might say, I'll draw my boundary here and say everything on the left is species 1 and everything on the right is species 2. Is that the idea? Is that right? So this is the common way theoreticians look at it. And it's a little bit related to how people do spectroscopy see it, because the spectroscopists are measuring properties of the stuff at the bottom of the well, because most of the population are atoms at the bottom of the well. So they're seeing properties, some property that's around here. If the atoms are in that arrangement, they'll give a certain color of the spectroscopy. And over here, they give some different color if they have this kind of geometry. Now, of course, if it had some geometry here, it would also give a different color, but I never see it because I don't have much population here. Because all the population is here or here. Is that all right? All right, so this leads to these pictures like this. Now, in this picture, to understand it, this parabola should be in and out of the plane. It's not in the same plane as this paper. And it's the directions that are not related to the reaction. So for example, on this plot, I could say, well, there's a reaction coordinate. I could travel from here to here. This would be my reaction coordinate. But I have dimensions perpendicular to it. So moving this way, I could vibrate back and forth in the valley. And this this distance is related to the width of the parabola up there on the slide. Okay, so that's what this picture is supposed to be showing. All right, and the same thing here. This one should be out of the plane, and it's corresponding to this one over here. So this is the vibration this way. Okay? And it turns out that the probability of being in these valleys depends on how many points are in the valley, how big the valley is. Because the probability is like the integral of that Boltzmann factor over all the possible r's that are down in the valley. So this big valley, if it's steep, it'll have a high probability of being here. And if this valley is a little bit higher and smaller, then it'll have a lower probability of being there. And so the ratios of those probabilities are related to the equilibrium constant. If we get the system to be a thermal equilibrium, then all these states will be Boltzmann populated, and the ratios of the populations of each valley would be proportional to the ratio of the Boltzmann factors. And the rates also have to do with the same thing. So as I get to the saddle point, there's still a vibration perpendicular to the motion on the reaction coordinate. And this might be bigger, wider, or narrower than it was in the valley. And if this is very wide, that means it will make the rate constant actually go faster, correspond to a higher rate, because there's more different pathways, many different pathways that all have low barriers, similar barriers that get to from the products to reactants. That would correspond to a higher rate. It's more probabilistic that would happen. So if this is very wide, that's drawn here, that would actually correspond to a relatively high rate. All right. So when I define them, I'm assuming I have a dividing surface, that there is some dividing surface that exists, or I'm defining it. I'm saying, okay, everything on the left I'm calling species 1, everything on the right I'm calling species 2. And then the rate is related to how much crossing I have across that dividing surface. So I can just count the trajectories as the atoms wiggle. If they cross the dividing surface, I can say a reaction occurred. So every time there's a trajectory that crosses the dividing surface, oh, species 1 turned to species 2. And then a little bit later, it wiggled back. Oh, species 2 turned back into species 1. Right? And I can count how many of the trajectories of all the possible molecules in my system, species 1s, what percentage of them turned into species 2. That would be proportional to the rate coefficient. And the analogy for this is if you wanted to figure out the change in the number of cars in New York City, you don't have to go around inside Manhattan and count every single car. You could just go count how many are crossing the tunnels and the bridges to get to Manhattan. And that total number that cross them must be equal to the change of the number of cars inside Manhattan. And it might be easier to count it that way at the toll crossings than it would be to try to go inside every garage and every apartment building in Manhattan and try to figure out how many cars were there. Does this make sense? Okay, so let's define a rate coefficient from New Jersey to New York City. And so we think that the rate coefficient should be proportional to the average number of cars entering the tunnels and bridges across the Hudson River divided by the total number of cars in New Jersey. And so that ratio would have the right units of per time. In this case, it's per day. All right? That's how you would define a unimolecular rate coefficient for population of cars in New Jersey going to New York. But if I wanted to measure it instantaneously, instead of trying to integrate over a whole day, I could try to measure it instantaneously. And the way I can do it is I could take photos of the cars at the toll gates for each bridge. So I could just take little photos. I could have a little camera set up on the toll gate, and I can see the cars going through. And in fact, they already have a camera there. So I can just take the photos that they take. But this would not be enough info. Just to see the cars at the toll gates is not enough, because a large number of cars could indicate there's a high flux from New Jersey to New York. Or it could just indicate I'm taking a picture of a traffic jam, and they're all stuck and they're not moving, in which case the rate from New Jersey to New York might be 0. Right? So just seeing the cars there is not enough to know what the rate is. But if I also did Doppler radar measurements to see their speed, then I would actually get a flux. I'd have the number times the velocity, and I could figure out the instantaneous flux. And then if I did that a few times randomly during the day, the average number there would give an average instantaneous flux, and that would be related also to the rate coefficient. So that's another way to do it, is instead of trying to do an integral over time, I can just try to do some instantaneous flashes by getting numbers times velocities. But I need to be careful. The dividing surface matters. So I drew the dividing surface here, but I could have drawn it differently, right? I could have said, oh, I think the dividing surface lays like this. And then I would actually get a different number for the instantaneous flux crossing it. And you can see the same thing happens with this. This is a photo, Google map of the George Washington Bridge. It's the main bridge between New Jersey and New York City. And there was a toll barrier there before at this location. And so that was, you could measure the flux of cars going from New Jersey to New York, crossing through this blue dashed line. And then you add up that for the other bridges and other tunnels, and then you get the flux. But you could have drawn those divided line in a lot of different ways. And in particular, you might have drawn it like this way, which looks okay, except there's this other road here. You see that? And so now I would get some things crossing this red line or coming from going to the bridge, and some of them might be people that are just going up this West Hudson River Drive, and they're going to stay inside New Jersey and never go across. But if I use this dividing surface, I would count them also as crossing the dividing surface, so I would get the wrong number. You got the idea? So now I need to spend some time to think about where's the correct place to draw the dividing surface to get the rate coefficient that I want. So you could also, this has to do with the definitions of what you're defining species as. If I say someone's going to New York, I could mean New York City, or I could mean New York State. Those are two different definitions of the species New York. And I would get different numbers because you can go to New York State staying on this side of the Hudson, because New York State extends over here. Just go up the Garden State Parkway and you'll get to New York State without ever crossing a bridge. So now this is quite the same as when I use the experimentalist definition of a species compared to, say, a theoretician's definition of a species. I can have a problem that they would both sound like they're the same species. They call it the same name, but they actually mean two different things. Just like two people might mean two different things when they say I'm going to New York. And theoretically, what you want is the dividing surface that has the clear definition of the species you want and gives the smallest possible instantaneous flux. That's the one that's the correct one to use when you're trying to get a rate coefficient. Okay, so once you've done all this, you now can derive the classical mechanics formula for what a rate coefficient is. And it's related to the fraction of species that crosses from region A to region B. So suppose we have a large ensemble of systems. They all have atom arrangements. We call them all species A, and we just grab geometries R from all of the space I call species A, so over species 1 over here. So all these different R's, I could choose this R, or this R, or this R, or this R. All these different R's are all perfectly fine. This is R1, R2, so many different R's. But all these R's I define as R's that are members of species 1, because they're all in this region. And each of them has different momenta. They can have momentum 2, and you could have had a momentum this direction, or this amplitude, right? There's many different possible momenta that they could have. But by the Boltzmann formula, both the R's and the momenta are constrained to be small, or favor small ones because of the Boltzmann weighting on energies. High momenta have high kinetic energies. The R's that are uphill have high potential energies. So the ones with down in the valley and have low momenta would be the most favorable ones and contribute the most. And I want to compute what fraction of those R's and P's convert into species B in a short period of time. And so I want to know which arrangement of atoms will actually move the R across the dividing surface. So now I'm going to call it species 2. And the expectation value of the rate coefficient is this fraction divided by the time I chose. And so I can use the same idea that I used in the toll plaza. I can say I want to get the instantaneous flux across the dividing surface. And what to do that is I just say, well, all of the R's that are on the dividing surface, I can get all these R's, and each one has a Boltzmann factor for its potential energy. And then they each have a distribution of P's. And each of these I can weight by their Boltzmann factors for momenta. And then I can add up all of the P's that lead towards from species 1 to species 2. And this is like taking the instantaneous camera picture. I'm seeing all these points that are crossing the boundary surface, and I'm also measuring their velocity. And each one I'm weighting by its Boltzmann factor. And if I add them all up together, that's the correct weighted sum to give the rate coefficient. Now we'll do it with algebra. So this is what the algebra, yeah?
They could be populated with a different distribution.
Yeah, so if I want to give a k of t, then I want to use the Boltzmann distribution. Sometimes k of t is not the right thing because they're not really thermalized, and then this won't be right. So this one is all just for the k of t. And to do it, so basically I need to define the boundary dividing surface, the dividing surface between A and B, and that's going to be some contour in the R space that separates the two. And I define it so if the Heaviside function of this thing is equal to 1, that means if S is positive, then this is equal, then I'm in region B. If S is negative, then I'm in region A. So S, this is S equals 0. S equals 0 on this dividing surface. And over here, S is less than 0, and over here, S is greater than 0. And that's, now I have like a scalar that's telling me whether or not I'm species 1 or species 2. All right? And then if I assume the Boltzmann population of all of those momenta, then I can write down the Boltzmann averaged flux from A to B. And this flux function is the key thing, right? So I know I want to do a Boltzmann function, but I need to have this correct flux function. This turns out to be the flux function. And I can do a whole bunch of algebra. Once I write this down, I can then do a bunch of like integrations by parts and stuff to reduce it to this form. And so it depends on how the dividing surface function depends on the positions. And then it depends on the velocities, which is the momenta divided by m's. And it's a Boltzmann average. And this thing still has a delta function in it, so I can simplify the integral even further. And so here it is. And if I simplify it and I do a coordinate transformation to these things called the normal coordinates, where I choose one special coordinate to be this direction that crosses, that makes S go from negative to positive. If I choose that as my special direction, and set that special coordinate has q equals 0 at the boundary, q star, then I can plug in for here and do the integral, and it turns out it's analytical. With that particular case, if the dividing surface is a perfect flat plane, and if I make this definition of the coordinates, then I can actually solve the whole thing, and I end up with very important equation. That's the transition state theory equation. And it says that the rate coefficient is just Boltzmann's constant times t divided by Planck's constant times the ratio of these two Q's, where the Q's are the partition functions of the transition state and of the reactant. And so this is just classical stat mech, and just based on that definition of what I mean by the species definitions, and assuming that I can make a planar hyperplane that's the dividing surface between the two. Now, in reality, the real dividing surface is not a plane. It's actually curved. But a lot of times, most of the flux goes through a very small area. And so using a plane to approximate a curve over a very small area is actually not so bad approximation. So a lot of times this works okay by using the dividing surface being as like a sum of hyperplanes, sort of like a piecewise approximation, piecewise planar approximation to a curved surface. So to do that, we just sum up over the transition states. Just like if you were doing the counting from New Jersey to New York, you would sum up over George Washington Bridge plus Holland Tunnel plus Lincoln Tunnel plus the Outer Bridge crossing. You'd add up all those different fluxes, and then the sum would actually be the total flux. It's the same idea. And then you can do the same thing in reverse. And what's really interesting and cool is that if you get the k from A to B and the k from B to A, the numerator is exactly the same thing. It turns out when you do the math, it's exactly the same quantity, the Q of the transition state. And then because of that, if you take the ratio of these two, the Q cancels out. And you just get that the ratio of these two Ks is just the ratio of the two Qs of the stable species, of the reactant product, not involving the transition state at all. And that's the quantity we call the equilibrium constant. So now, just from a couple Qs, we can get both the rate coefficients forward and reverse, and also the equilibrium constant. So this is the main idea for how we can go from first principles to get rate coefficients, is all we have to do is figure out how to compute these Qs things. And that'll be a later lecture. We'll talk just about that computation. There's a lot of details in this. Yeah.
Is there any way to correct the transition state theory to account for quantum tunneling from one state to another, from one side to another?
Yeah, it is, but it's kind of complicated. Yeah, maybe later I'll get to that. Yeah. So the real systems are quantum mechanical. So the classical mechanical way I did it is not true. So in particular, these quantities, the Qs, I wrote them as a classical phase-space integral. Let me see, here it is. This Q is just this integral, and all you need to know is the V, and you can get it. You just have to know the shape of the potential, of the interaction potential of the atoms, and that's it. But this equation is not true in quantum mechanics. And first of all, things are quantized, so it's not a continuous integral, but actually you have to do a sum instead. And then secondly, there's tunneling, and so there's like another whole complexity of that. But you can still define a quantity. You would call Q as like the quantum mechanical analog of the classical mechanical Q. It's just more complicated to calculate. And that's, so that's what we'll do when we actually try to get the rate coefficients. And in the molecules, the translation of molecules is basically classical. So molecules are heavy enough that their translation is more or less classical, and you can use the classical formulas okay. The rotations are not quite classical, but sort of like classical, and you can get a Q expression that looks kind of like the classical one, and it's good enough. Vibrations are completely unrelated. Quantum mechanical vibrations have nothing to do with classical vibrations. And so all the vibrations, we have to do a completely different way. And we'll talk about that. And then tunneling has no relation to anything in classical mechanics, so you have to do a whole separate story about that. Despite the fact that this is super complicated, and it's definitely very complicated, The calculations are doable. You can do them, and they're accurate enough. You have to make some approximations. Like I made the hyperplane approximation. You have to make some other approximations too along the way. Despite all that, they still turn out to be accurate enough, similar enough to the real reactions, that the numbers you get are pretty close to what you actually measure experimentally. And you can do the calculations for small molecules and do them really fast, often faster than you could even order the chemicals and get them from the Sigma Aldrich to get them to come to your place. You could do it yourself and figure out the calculation. So it's very beneficial that you can calculate them. All right, so key points. To predict the kinetics of a system, you need to know what's present. You need to know what reactions are important. And you need to know all the parameters, thermo and rates, and also transport and other stuff too. Unfortunately, we don't know it all. And so our kinetic models are always going to be approximate. And in fact, we don't even know what all the species are that are present or all the reactions. So our models can be pretty far off. And often what happens is we end up with multiple models for the same molecules, sometimes for different purposes, sometimes just by mistake, sometimes because we're part of the iterative procedure of trying to get them better and better. You need to think carefully about how you define the species in your model. Ideally, you'd like a clear way to go from the species in your computer model to the definitions of the observable stuff that you're going to really measure. And you need to be able to explain that very clearly, because you might want to be, your model might be used by some experimentalist, and they want to be able to check if your model is true or false. But that means your model has to make an unambiguous prediction of something that they can measure. And a key part of that is defining what the heck the species are, so that they would know what they're even trying to measure. And then even in this species, more subtly, the way you divide the species from each other affects the calculation of the rate. And it's not that hard to screw it up. So you have to worry about how you define exactly what you mean by a species and how you're going to define separate of different species. But once you've done it, the math is straightforward, and you can end up with this nice transition state theory formula. And in fact, this was derived 1935, I think, by Eyring first and by a couple other people. There's a very nice derivation by Wigner about it from a long time ago, so almost 100 years ago. This was worked out. So we have the formula, and in fact, people have done the calculations correctly, and they compare to experiment. And I would say typically within a factor of 3 is not unusual between how you would calculate this way and what you would actually measure. So you can do it pretty well. But it's a lot of details to get right if you want a factor of 3. All right, so that's that. And since we have a few minutes left, let me just start the next one, and then we'll break. So let's just get back to real chemistry. All right, good. So let's talk about real chemistry. What do we care about? As we said, we have different models for different regions. And one region we always have in combustion is the high temperature exhaust region. And that's going to be in that region, we expect that a lot of reactions are going to be equilibrated. And so it's really going to depend a lot on the thermochemistry. It's sort of after you've done most of the reactions, you're basically going to be in a case where you're basically at equilibrium. So back up to our summary of where we were, fuels are like a boon and a bane. They're like very beneficial. They provide all the goods of modern society. Basically, 80% of all the energy we use for everything is coming from burning fuels. We have, they're very inexpensive. It's really great for the economy. We get a lot of benefit for not much money. But it's not sustainable, and particularly from the point of view of greenhouse, but also in other ways. And so we need higher efficiency, we need new energy carriers, we need something, we're not sure what. But we can't just keep going the way we're going. Fuel chemistry turns out to be really tricky and complicated. As we wrote for hydrogen, just hydrogen and oxygen, we already have 10 reactions with 10 different rate coefficients. That means it's not going to have even a single Arrhenius form. If you plot what happens, it's actually really quite complicated how hydrogen and oxygen burn together. And if you go to other fuels, it gets worse. And there's a lot of intermediates between the fuel molecule and the final products. So it's not just like hydrogen and oxygen react to make water. It's like hydrogen and oxygen react to make a whole soup of different radicals, and they do all kinds of stuff and eventually make some water. And this turns out to give very nonlinear kinetics. So even though each step is linear or bilinear in concentrations, by the time you string them all together and get the overall effect, the whole thing can be extremely nonlinear. And therefore, the details really matter, and it can be quite confusing. And hard to interpret experiments also, because you typically measure just at like a small range of conditions. You're trying to understand more global understanding from just this little bit of information you have. And you can just, you've seen this yourself in real life. So how many of you ever used a gas stove? Anybody ever use a gas stove? Or propane stove? Like a burner, you have to light it? Yeah, okay. Yeah, okay, so almost everybody in this room has done this. So you've observed this. If you turn on the gas and you don't light the spark, what happens? Nothing, right? The gas just goes in the room, right? If you turn on the gas and then you light the spark, what happens? Yeah, you see something go whoosh, and then you have a fire, right? The temperature in case A and case B are like really different, right? If you want to boil water, the first one's not going to work, right? Right? The second one, if you put your hand in there, you're going to be burned. What's happening is that the room temperature mixture is stable, and there's really negligible reactions. You can put gas in the air. It does react, but it's like many days it takes methane to react in the air. So it's basically not reacting. As far as you can tell, you wouldn't be able to detect it. But if you put the spark in there, you can detect it. It's definitely a reaction, right? You feel all this heat coming out. And you can get an explosion. Like, it's definitely possible, right? And you've probably heard of this, right? People can have, if they have a gas leak for a long time and they light a spark, you can kill people, right? It can be pretty bad. So the chemistry can really change by just a very small perturbation. In that case, a little tiny spark can like make a whole house explode, right? In the worst case. And in your gas case, it's still you have a region maybe a few centimeters across, suddenly goes from doing nothing to all of a sudden it's done a lot, where you've got tons of reactions and you get the final product CO2. If you do this and you carefully maintain the temperature low enough, what will happen is you'll make a whole bunch of aldehydes and peroxides. And so that's also, you can measure that experimentally. If you just put some methane and some oxygen together and you're in a certain region where it doesn't really make a fire, you can make a whole bunch of other stuff. And then if you do it and you make it where you're rich, where you have a lot of gas and not very much air, you won't burn it to CO2. Instead, you'll burn it to carbon monoxide, CO, and you'll make a bunch of hydrogen. And then if you make it even a little bit richer, you'll actually see black powder form. You'll make soot, you'll make benzene, you'll make acetylene, all kinds of stuff. So it's the same chemical comes in, it's just methane and oxygen. And somehow, just by changing the conditions a little bit, the composition or the temperature, you can like wildly change what happens. And this is just a manifestation of how complicated the chemistry really is and how nonlinear it really is. So then you have to worry about all these different regimes of how things can happen. You can have the exhaust region where after it's burned, the temperature is super high, and mostly it'll be equilibrated there. And so therefore, it's mostly the thermo that will determine what you have. You can have pre-mixed flames, like in a gasoline engine. And there you'll have like a flame front propagating. You have fuel and air mixed. Let me draw a little picture. So in your gasoline engine, there's a piston. Here we have fuel and air. It was all with fuel and air all mixed up together. And so you have a spark plug. And a little spark came out. What will happen is that this region right here will be CO2 and water and nitrogen from the air. right? That's what will be there. And here will be fuel and air. And this flame front is propagating in to convert the fuel and air into exhaust, right? So that's how that works. If I have a diffusion flame, that's where I have the fuel and the air separated from each other. Then right near the boundary where the air and the fuel are touching, you'll get a flame. And the fuel and the air have to diffuse to that flame front. And what happens there is you get fuel pyrolysis first before it reaches the flame front, because the fuel is like moving very slowly towards the flame, and it's feeling a lot of heat, and it'll react on the way there. We'll talk more about partially premixed flames. This is actually the most common type. So a lot of combustors and diesel engines both work this way, where you have some fuel air mixing, but not enough air to burn it all the way. And so then you have a premixed flame, then you have fuel pyrolysis, then you have a diffusion flame when you reach the rest of the air. So it's kind of complicated. But very important. And then you can have pre-ignition chemistry, so you can have stuff, fuel and air mixed, and before anything happens, any spark, you just have spontaneous combustion, and the reaction happens. That's super complicated too, and we'll talk about that. Let's do C. So pre-mixed, let's just talk about that. This is a simple case. The fuel air mixing has a lot of advantages. You can make the mixture lean enough, that means enough air, that you won't make pyrolysis. Basically, you'll just make the final products to be CO2. And you can also add a lot of air, and that will reduce the final temperature because the nitrogen in the air gives extra heat capacity to make the temperature lower. And that will have the effect of reducing the amount of NOx you form, because NOx is a very high EA process. And so gasoline engines work this way. So they stoichiometrically mix up the fuel in the air. And then they mix a lot of NOx because it's stoichiometric, the temperature is actually very high. But they have a very nice emission control system called a three-way catalyst, and that gets rid of most of the NOx. And they control the ignition timing by the spark, and that controls when it burns. And so you can make it burn at just the right time to go in time with the piston motion. And then how fast this burning happens is the intrinsic flame speed of this mixture, and it's affected by how wrinkly this flame sheet is, which has to do with the turbulence in the system. And running stoichiometric this way, they do it because I lost my pointer. Here we go. They run stoichiometric so that the three-way catalyst will work. It turns out the three-way catalyst only works in a very narrow range of compositions, and it's near stoichiometric. So they run it stoichiometric to help the catalyst work, and it maximizes the power, so that's great too, but it removes the control knob, so you don't have any knob for controlling how much air you're adding, because you have to lock it to match the amount of fuel. And this is a problem when you try to run it low power, because what happens is the only way you can lower the power is reduce the amount of fuel and air in the mixture, which means lowering the pressure. If the pressure gets down to below atmospheric, you're actually running a little vacuum pump. And so you're going to have to waste energy running a vacuum pump. And so that's a disadvantage of the gasoline engines. So fuel and air fuel air mixing can be good, but they're intrinsically unstable and kind of dangerous. Because if you get a spark in there, just as you saw with your gas burners, boom, right? You have a fire. And this gets pretty bad. And so because of this, they're not used that often. So gasoline engines use them, but it's really not that common to do this because it's dangerous. And also it's an example of how inhomogeneity can form spontaneously. So you have what you think is a perfectly uniform fuel-air mixture, and then if you look at it after an instant, some part of it might have ignited, and all of a sudden it's at 2,000 degrees Kelvin, while the rest of it is still quite cold. So it was uniform, and all of a sudden it's completely non-uniform. And so this is one of the bad things about combustion is instabilities. And maybe some of you were taking the instability class. There's a lot of different ways the systems are unstable, and it could cause a lot of problems sometimes. All right, I think I'll just stop by showing a picture of the structure of a premixed flame. So on this side is the fuel and air. So here's, in this case, it's methane, fuel and oxygen. And this side is the products, water and CO2. And you can see the temperature suddenly jumps up in the flame front. So this region right around here is the flame front where you have a lot of radicals and you have a lot of chemistry happening. And you can see everything changes pretty fast, orders of magnitude in just, this is like only 1 millimeter. From here to here is a millimeter. So in way sub-millimeter, you completely change the whole composition and the temperature. It changes by 1 millimeter, 1500 Kelvin jump in temperature. So it's pretty big temperature gradients. The rates, because of this temperature changes so much, the rates change by many orders of magnitude. So it's just quite numerically complicated to model what's happening. So we'll start next time with just looking at what happens over here when you're near. You've already burned the stuff up, and now you have exhaust at high temperature. And in that case, it'll mostly be thermally equilibrated. And so we'll try to figure out what's happening there. And then later we'll come back to what's happening over here. All right, well, thank you for your attention, and I look forward to seeing you tomorrow.